Up here on the screen is a typical problem that I would put on an exam. Why do I like a problem like this? Because in one 25-point problem, I think this is actually worth more than 25 points, this one is. I think this is worth 30 points. I can ask you multiple things. I'm asking you polytropic processes, constant pressure processes, first law, cycles, all of it comes into one problem. I don't know if I've said this before. I think I have. But if you don't see a problem like this on your exam, something happened to me. Call me, check on me, make sure I'm okay. Okay, because I like this. Now really, I could only ask this problem on the exam and probably cover everything. But that's not what you want. You pay good money for this class. You want 4 solid questions that challenge your ability to understand that you know thermodynamics. You want to show me, Wanklin, here is what I know about thermodynamics. And one measly problem would not do that. You want 4 quality, developed, well-rounded problems. And that's what you will get. Okay, I promise you on that. I was reading my T-vals for the summer last night because they were released, and they said, Dr. Wanklin gives exams just because he likes to watch us suffer for 2 hours. And that is correct. I get my evil superpowers from your pain. It strengthens me. It makes me powerful. That's the only reason why I do it. Okay? Now, if you don't, that is sarcasm. That's not what I do. Because what will happen now is somebody will record this video and they will take out this little portion of it and they will repost it, give it to the dean and say, this is what Wanklin does. Listen, what I want to do is I want to challenge you. I want to make sure that you know your stuff. I'm going to ask you problems that are not just plug and chug regurgitation, memorized things that show that you think. And this is one of those problems. So let's do it. Okay, 2 pounds of a gas in a piston cylinder, closed system, assembly, undergoes a thermodynamic cycle consisting of 3 processes. Process 1 to 2, specific volume 1 to 2 is, and specific volume 1 is the same as the specific volume 2. By the way, I can't say specific very well, I have a stutter. A specific volume 1 is equal to specific volume 2 is equal to 4.434 cubic feet per pound mass. The pressure at 1 is 100 psi. The internal energy at 1 is 1,105.8 BTUs per pound mass, and the heat transfer 1 to 2 is equal to minus 581.31 BTUs. Process 2 to 3, I know that the pressure from 2 is the same as the pressure at 3, which is 60 psi. The specific volume of 3 is equal to 7.82 cubic feet per pound mass, and the internal energy at 3 is 1,121.4 BTU per pound mass. Process 3 to 1 is a polytropic process. There are no changes in kinetic and potential energy in this process. So the first thing I want to do is sketch the cycle on a PV diagram labeling the direction of the processes. All right, so I'm going to go over here and I am going to draw a PV diagram, pressure, specific volume, and the pressure axis is going to have PSI, and the specific volume axis is going to have feet cubed per pound mass. Okay? I have to look here. I know that pressure 1 is 100 psi. And specific volume 1 is 4.434. So I'm going to 4.434. This is my point 1. I don't know my point 2 directly from this. It says here, I know my specific volume 2 is the same as 4.434. So somewhere along this line here, I'm going to get my point 2. I don't know exactly where it is from reading process 1. But if I go into process 2, I see, look, pressure 2 is equal to pressure 3, which is equal to 60 psi. So I'm going to go down here and I'm going to label 60 psi. And now I know that pressure 2 is 60 and specific volume 2 is 4.434. And so I am going to label this as point 2. And the direction of the process is straight down. The next thing I'm going to say is pressure 2 and pressure 3 are the same at 60 psi. And my specific volume at 3 is 7.82. So I know that I'm going to go over here to a point that's 7.82. And that is going to be my point 3, constant pressure going over here. That's my point 3. And then coming back 3 to 1 is a polytropic process. I don't know exactly what kind of polytropic process it is, but I'm going to say there's going to be a curved line that's going to go between 3 and 1, and there we go. That is my cycle sketched on a PV diagram, labeling the direction of the processes, also labeling all the states, making sure I know this. This is good to have, to see, to know where I am. Drawing a picture is very important here, and that's exactly what I will have you do. Okay. Second thing is, find the value of n for the polytropic process 3,1, as in PV to the n is equal to constant. Okay, so now we know here, for 3 to 1, which is a polytropic process, we know that P3 specific volume 3 to the n is equal to P1 specific volume 1 to the n. Now notice I use specific volume instead of volume, and there's absolutely nothing wrong with that. If I wanted to, I could do the uppercase V, the total volume, but remember, even though I said PV to the n is equals to constant, P times specific volume to the n constant is the same thing. It's the same thing. Same type of polytropic process. Okay? Now, when I look at this, and if I did put this in here, if I put that volume to the n is equal to mass times specific volume to the n, the masses would cancel because it's the same in point 3 and point 1, so it would give me the same thing. Okay, so what do I have here? I'm going to do some solving here. This is like a homework problem that you had. P3 all over P1 is equal to V1 all over V3 to the n. I want to get rid of that exponent, so I'm going to take natural log of P3 all over P1 is equal to n times the natural log of V1 all over V3. And I can solve for n there is equal to natural log of P3 all over P1 times natural log of V1 all over V3. Okay, just a little rules of logs and doing some algebra there. And we know all these values, and it's easy to refer to our diagram, so we can say this is going to be natural log of P3, which is going to be 60, P1, which is 100, all over natural log of V1, which is 4.434, divided by V3, which is 7.82. And I'm going to save us some time by not plugging it into the calculator, but you should get, when you do this, 0.90. That is going to be my n value. I'm going to box it, and I'll be done with it. Any questions on that part? Okay, we have now found the value. Now, just to note here, these little numbers here, 4 and 5, that's the point values for this on the test. I'd like to give you point values so you know what things are worth. Then it says completely fill out the table below. Oh, the table below disappeared. So let me show you what the table below looks like. The table below looks like this. It's going to ask for the change in internal energy, the heat transfer, and the work in all in BTUs. So it's going to ask us to fill out this table. I do this because it's easy for me to grade so I can see what's going on here. This is going to be process 1 to 2, process 2 to 3, and process 3 to 1. I need to fill out this table. Now, I'm going to have to approach this systematically. So let's see what I can do for that first row. And I'm sorry here, I'm going to have to keep scrolling up and down. That's just the kind of way this goes. I wish I could do something where it continues on to this next screen. That would be beautiful and wonderful, but unfortunately that's not the way this works. It tells me here in the problem statement that Q12 is equal to negative 581.36. So I'm just going to put it here, minus 581.36. Okay, there we go. It also tells me that the specific volume of 1 is equal to the specific volume of 2. Because that is the case, and because I can see in my diagram, I know that if the specific volume is the same, it's constant volume, and constant volume work is equal to 0. So I'm going to put 0 there. Nothing else I can really use from the processes here directly. You probably can fill out this empty box here, but let's go through the formal process of doing that, because for each one of these processes, there's going to be a first law. Delta U12 is equal to Q12 minus W12. Delta U34, delta U23 is equal to Q23 minus W23. And delta U31 is equal to Q31 minus W31. Okay? Each one of those equations has to be valid for each process. Has to be, has to be, has to be. Now, I notice that I have Q12 and W12 for the first equation. That leaves me with one unknown. So I'm going to solve that equation. And I'm going to say my unknown, delta U12, is equal to minus 581.36 minus 0. And that leaves me with the delta U12 is equal to minus 581.36 BTUs. And so I'm going to put it here. I have completely solved the first, or filled out the first row. Okay. Now the second row. Now I can circle this one, say that I got that one done. Now the second one, let's look at what it says. It says to me, P2 is equal to P3, so I have constant pressure. V3 is equal to 7.82, and U3 is equal to 1,121.4 BTUs per pound mass. Well, the only thing I really know here is that I have constant pressure work, and I can see that here on the diagram. So I have constant pressure work. Let's see if we can calculate the constant pressure work. So for process 2 to 3, I know my work is equal to the integral of P dV, or that's the integral of P times mass times the change in specific volume. And so I know that pressure is constant, so it comes out of the integral, and mass is constant, so it comes out of the integral. And if I integrate this between 2 and 3, I'm going to get specific volume 3 minus specific volume 2. And I know every one of those things. I know every single one of those things, so now I can find out what my work is. So I'm going to write it this way. My mass is 2 pounds mass. My pressure is 60 pounds force per inch squared. My specific volume 3 is 7.82. My specific volume 2 is 4.434, and this is going to be cubic feet per pound mass. That's the equation, plugging and chugging it. Now I have to see about units. Does it make sense to me? Well, I know here there's going to be some unit issues that I have to deal with. So pound masses are going to go away, cancel out. I need to have this in BTUs, right? I have to have this in BTUs. That's what my table up there has, is BTUs. So I need to do some conversion. And so the first conversion I'm going to do is I'm going to say there are 144 inches squared in 1 foot squared. And so now that gets rid of inches, and it gets rid of some of my feet, 2 of my feet, and now I have pounds force feet, and I remember that the conversion is 778 pounds force feet is in 1 BTU. Pounds force feet. Now I have my units of BTUs, which is exactly what I want, and so I can now calculate it. Plug everything in, check the units, then calculate. Please follow. Please make sure we do that. This is going to give me 75.21 BTUs. And I should look at that and think that makes sense to me. I am expanding from state 2 to state 3. Expansion is occurring. I am acting from the system onto the surroundings. Okay, that makes sense to me. 75.21 BTUs. I'm going to go ahead and go up here and write it in my table. 75.21. Okay, now I have this piece of information. I don't have enough information to solve anything else here. I look up here, I need to have U2 minus U1. Well, I have U3 and U1, but I don't have U2. I don't have any information about heat transfer. So don't feel like you have to go boom, boom, boom and solve every equation. We don't know enough there. So let's move on. Let's move on and see if we can do anything with the third equation. The third equation, delta U31 is equal to Q31 minus W31. Okay, well, I can find out what delta U31 is. Okay, I know that delta U31 is equal to the mass times U1 minus U3, and I have been given each of those things in my problem. So I can say this is equal to 2 pound mass, and my U1 was given to me as 1,105.8. My U3 was given to me as 1,121.4 BTUs per pound mass. Okay, I'm going to be able to cancel pound mass and get BTUs, and that number is going to be negative 31.2 BTUs. Okay, so I'm going to take that negative 31.2 BTUs and I'm going to put it up into my chart, my table, negative 31.2. Okay, now there's a couple paths I could take to solve this problem now. I now know or can figure out what the internal energy change from 2 to 3 is. That is because we're dealing with a cycle. A cycle says that the internal energy change, total internal energy change, when I add up all these things, has to equal 0. U12 plus U23 plus U31 has to equal 0. And so, since I have 2 out of the 3, I can find that missing one and plug it in, and that's exactly what I'm going to do. So I'm going to say delta U12 plus delta U23 plus delta U31 is equal to 0, and that's going to be negative 581.36 plus delta U23 minus 31.2 is equal to 0. And this gives me that delta U23 is equal to 612.56. Now again, I didn't have to solve it this way. I could go on and work on it in a different method, but this is how I see it. It may not be how you see it. 612.56. So now that I have this, 612.56, I now have in my second first law equation, my first law equation for process 2 to 3, now I have 2 out of the 3 values I can solve for the third. Okay, so here we go. This is going to be 612.56 is equal to Q23 minus 75.21. And so solving for Q23, I'm just basically going to add this over here, and I'm going to get 687.77. And now I've completed the second line. By going into the third process, I've completed the second process. Okay, we still have 2 more boxes to figure out here. So if we go figure out those other 2 boxes, we're going to have to say, all right, I don't know exactly what Q31 is, but I do know that the work from 3 to 1 is a polytropic process with n is equal to 0.9. So I have that information. So I'm going to say that the work from 3 to 1 is equal to pressure 1, volume 1, minus pressure 3, volume 3, all over 1 minus n. This bothers students because they'll look at the equation sheet and it'll say P2V2 minus P1V1 over 1 minus n. What it's trying to say is pressure final, volume final, minus pressure initial, volume initial over 1 minus n. Maybe that's how I should write it up on the equation sheet. That would probably be a better thing for me to do. In fact, I need to do that. I don't know why I haven't done that until now, but maybe I should do that. So here, the final is 1 and the initial is 3. That's why we put it this way. Now, I gave you volumes here. The problem statement has specific volumes. So I'm going to write this as mass times P1V1 minus P3V3 all over 1 minus n. Okay, and now we're going to plug things in. It is 2 pounds mass. P1V1, 100 pounds force per inch squared. V1, 4.434 cubic feet per pound mass. Minus P3, 60 pounds force per inch squared. V3, 7.82 cubic feet per pound mass. Divide that by 1 minus 0.9, because that's the exponent we found. Now let's just pretend that you messed up the exponent in part A. So you messed up the exponent in part A. I'm not going to count off this equation because you messed up it at part A. If you mess it up and you're using the same thing that you calculated in part A, or part B actually, I'm looking for your process. Okay, I have an Excel spreadsheet that I'll type in your exponent. If your exponent's value would work out this equation the way it's supposed to, you're going to get full points. Okay, I'm not going to keep having a domino effect for you. Okay, let's look at the units here. Pound mass is going to cancel. We're going to have that same issue up here with our inches. So we're going to have 144 inches squared is 1 foot squared. So that's going to go, inches are going to go away here, inches squared are going away, and some of our feet are going to go away. And now we have to do that, our old friend, 778 foot-pounds is in 1 BTU. Okay? This is going to convert everything to where we need it to be. And so our answer here is going to be negative 95.51 BTUs, and that makes sense that it's negative because we are being compressed. We are going from a higher specific volume to a lower specific volume, so the surroundings are acting on that system. It should be a negative number. Negative 95.51. And so I will put this up here as negative 95.51. Now, I have a choice again about how I'm going to solve for this open number Q. 2 ways I can find it. Okay, I can solve the first law for the last process and find the empty value, the missing value. Or I can understand that this is going to be that the summation of the heat transfer minus the summation of the work has to equal 0, and so that the summation of the heat transfer has to equal the summation of the work. That's for cycles, and for cycles only. That's the thing. So I can take advantage of either of these two. I am going to go and use this relationship to help me out. So when I find this, I'm going to say that Q12 plus Q23 plus Q31 is equal to W12 plus W23 plus W31. And what do I have? Negative 581.36 plus 687.77 plus my unknown Q31 is equal to 0 plus 75.21 minus 95.51. And that gives me Q31 is equal to negative 126.71 BTUs. I'll plug that in. Now the good thing about these problems, we did a lot of work here. We've been working for about 25 minutes on this problem. It's a big problem. We can check our work because all the first laws have to equal. And we know all the columns. We know that delta U has to equal 0. We know that delta Q, or sorry, not delta Q, summation of the Q has to equal the summation of the work. That has to equal. And if we have a mistake there, if those don't equal, we've made a mistake. Okay, so we could check that if we wanted to. But this is negative 126.71. Okay, that's part C. Part D says, is this a power cycle or a refrigeration cycle? How do we know? If what is positive? If work is positive, it's a power cycle. If net work, cycle work is positive, it's a power cycle. If cycle work is negative, it could be either a refrigeration cycle or a heat pump. This problem is asking us, is it refrigeration or power? So all we're looking for is if the summation of the work is positive or negative. You can see here that 75 minus 95 is going to give us a negative value. So this is a refrigeration cycle. This is a refrigeration cycle. Now, there are students that have looked for refrigeration cycles by trying to figure out what the heat transfer is. It has nothing to do with the heat transfer. Nothing to do with the heat transfer. Okay, it has to do with the net work. Okay, make sure you understand that. There's other things that are keys about this, but we haven't got to that yet. Right now, all you need to understand is if it's positive, it's a power cycle. If it's negative, it can be either a heat pump or a refrigeration cycle. Are there any questions about this? Yes? What if network is 0? I made a mistake in the way I've created the problem. In a cycle, you want it to have you want it to do something, and that's going to mean that the work is going to be a value. I'm trying to think if there's a network is equal to 0. Nothing's happening if that happens. Any other questions? Yes? What if we have to determine it between a refrigeration cycle and a heat pump cycle? You won't. In this case, you won't. Because you can't tell. Right now, you cannot tell with what you know in this class. You can't tell. So I'm not going to ask you to. All right, let's go down to these other problems here. Now these next problems are the problems that I give to you and I tell you what type of cycle it is and I ask you to find some things in it. If there is one thing that I want you to do in practicing for this test, I want you to go. I have posted 25 pages of old exam material on Canvas. I posted a study guide. Look at the old exams and pick out the problems here where it talks about specific cycles and read through them. The math is not hard about them. The analyzing them and determining what they mean, what they're trying to say, that's the hard part and can really cause some issues here. So let's read this one. It says, a refrigeration cycle operates with a coefficient of performance beta is equal to 1.5. Okay, so what do we know? We know beta is equal to what we want over what we have to give. And with a refrigeration cycle, we want cooling, which is Qn. And what do we have to give is power, which is work of the cycle. Okay, that's what we have to give there. This is on your equation sheet. You don't have to worry about it. What they did here, they said, okay, now for the cycle, Q out is equal to 50 kilojoules. Well, I don't have Q out in any of this equation. So I have to do some manipulation here. All right? I know that work of the cycle is equal to Q out minus Q in. I know this, and this is actually magnitudes, so I don't have to worry about it. When we derived it, we took care of all our signs, so we don't have to really worry about that. And now, I know some things here. I know that 1.5 is going to be equal to Q in all over 500 minus Q in. Now I have one equation and one unknown. And now it's just algebra. Okay, I'm going to get 750 minus 1.5 Q in is going to equal Q in. I'm going to get 750 is equal to 2.5 Q in. And that gives me that Q in is equal to 300 kilojoules. Done. But I had to understand what the problem statement was saying, and I had to understand how the work of the cycle was created for a refrigeration system. That is part A. Part B is, what is the work of the cycle now? Well, work of the cycle is Q out minus Q in. It's 500 minus 300, which is equal to 200 kilojoules. That is the work of the cycle. If you would have put on this minus 200, I would also accept that, because you would know that I was intending to add for magnitude, but I wasn't specific enough. So that's work. A refrigeration cycle is adding work to the system. But wording is important. In refrigeration cycles and heat pump cycles, the wording is kind of can cause some problems. Power cycles is pretty straightforward. One of the problems I think on the practice exams that you're going to see is a water fountain. Okay, let's talk about a water fountain. A water fountain. If I say a water fountain's water is cooled by removing 700 kilojoules of energy from the water. For a refrigeration cycle, is that 700 kilojoules Q out or Q in? We have a Q out. Anybody else want to support Q out? How about Q in? Anybody want to support Q in? One lonely hand looked like it was coming up, but then went to the right here. It is Q in. Why? That's because this is a common thing. What is happening? The refrigeration cycle, the water cooler, the water fountain. The water is coming in there, and the heat from the water is going into the refrigeration cycle to be taken care of. The refrigeration cycle, if you are the perspective of the refrigeration cycle, you're taking heat out of the water to cool it down. That's Q in. Okay, that's Q in. Then you're messing around with that heat, and then you're dumping it out as hot out the back end of it. Make yourself the refrigerator. You are the refrigerator. You are the cycle. Because when you see this, and I'm totally with you here, when you see, it said the water is losing heat. Losing is out. Okay? It's out from the water, but into the cycle. Okay? You won't make that mistake on the exam. That's what we need to do. Okay, so let's ask this question here. A heat pump cycle delivers energy by heat transfer to a dwelling at a rate of 60,000 BTUs per hour. So a heat pump provides heat to my house at 600 BTUs, 60,000 BTUs per hour. Is that Q out or Q in? You got it. It's Q out because a heat pump cycle is dumping out heat to a dwelling. You're not the dwelling. If you think about the dwelling, it's coming into the dwelling, but you're the cycle, you're pumping it out. Okay, so make sure that's the case. The power input to the cycle is 7.8 horsepower. Determine the coefficient of performance. Okay, gamma is equal to what we want over what do we have to give. Well, what we want here is Q out, and this is a rate problem, so it's Q dot out over what we have to give is our power. So we're going to have 60,000 BTUs per hour divided by 7.8 horsepower. But remember, gamma is a unitless number. We cannot just divide these. They have to be the same units. And so we're going to have to go to our conversions and say 2545 BTUs per hour is 1 horsepower. And then we can do the calculation, because then we're going to have horsepower over horsepower, and we're going to get gamma is equal to 3.02. Okay, next thing it says here. Evaluating electricity at 8 cents per kilowatt hour, determine the cost of electricity in a month when the heat pump operates for 200 hours. Okay, this is the only time in the class where I'm going to ask you to convert from English units to SI units, because we pay for our power in kilowatt hours. That's what we do. So I know here that I have 7.8 horsepower, and I want to know how many kilowatts that is. And so I go to my conversions in my book, and I know that 1 horsepower is equal to 0.7457 kilowatts, which is 5.8165 kilowatts. That's how many kilowatts, that's the power I'm using, I'm requiring. Power is energy per time. How much time? That's going to be 200 hours. And so this is going to give me that my energy is going to be 1163.29 kilowatts times hour. That's how we give this, that's how we give electricity. You have to think through the process. What is it asking me? What am I trying to work with? Okay, and now we know that this is 8 cents per 1 kilowatt hour, which is $93.06. That's how much it's going to cost to run that heat pump. I will say this again, because it's an important thing. These problems are not difficult mathematically. They're difficult conceptually. They're difficult reading the problem statement and understanding what I'm asking you for. And I think through this problems, your homework problems, and then the problems I've given to you on my practice exams or my old exams, you should be able to put yourself through some sort of mental gymnastics and to kind of get these things worked out. Try not to overthink it. Try to think, I am the cycle, what's coming into the cycle, what's going out of the cycle. If you put yourself in the terms of the I am the cycle, you should be okay. When you're working on the practice exams, if you start to work on those, you're not going to do all 24 pages or 25 pages of them. Maybe you'll take a single exam there and say, I need to be able to do this in 2 hours. But every page is designed to be done in about 30 minutes. So get into a real situation. Get out a piece of paper. Get out your equation sheet. Get out a timer. Put you under a time cap. See how you can do it. Okay, that's what I would recommend doing. Are there any questions here before we let you loose for the weekend? Okay, if you haven't done so already, please print out your appendices. Our next in-class session will just be using those over and over and over again, okay? Till then, have a good weekend, and we'll see you on Wednesday.